So in the last few lectures, I was talking about various types of Boolean problems and what can be done to solve them both in the classical language and then converting to a quantum language. Today I'm going to pick up a new topic, and that is also an algorithm, but which turns out to be much more powerful than just the Boolean algorithm. And the problem is that of database search. And it has a wide range of applications. The most familiar to you today is you just type something for Google to find out. Okay, how does it do it? That is essentially the problem. And it turns out that there is a classical way of doing things, which is what Google does. And there is a quantum way of doing things, which is, well, applicable to a large number of possibilities. We'll see where all that can take us. But the quantum strategy is more powerful than the classical one. How powerful and what do we really need to implement that? That's a part which I will go through in details. But let us first just look at the way the problem is tackled in the classical scenario. So, what do we have? There are a set of objects which I just call xi. And these objects have some property. Okay. Which I will call some function. We don't know what this function is or how it is calculated, etc. But we are given the value of the function, and the job is find the object. So the value of the function might be just a kind of a string which we type in the Google search box, or it can be specified in different manner. But I will give this label because it is often referred to as a target. So xt is the target. What you are given is some property of the function, and this falls in the category of what I had called relativized problem. Given a particular way in which you can evaluate this function, find where it came from. So what do we do? There are various techniques, but before I go into that, let me give a simple example which most of you would have kind of encountered in the school days, that there is a competition between two teams to find a name of a famous person. Okay, so one team chooses the name of a famous person, the other team's job is to find out what that name is, and the constraint is that The second team will ask certain questions to the first team, but the answer which will come back is binary, yes or no. And of course, the teacher has to act as a referee so nobody cheats. So how does it proceed? Well, you can ask a direct question that, is the name Albert Einstein? And in most likelihood, it will fail because there are lots of possibilities and you are just picking a random one inside there. It's not going to give you much information. So people quickly learn how to organize the set of questions. You ask a question, is the person dead or alive? What is the purpose of the question is, irrespective of the answer, the search range becomes narrower. Okay. So whether it is dead or alive, now you have to look for only a smaller number of possibilities. You can ask another question. The person a man or a woman? Okay. Another narrowing of the search, and that will take you to the target in a certain manner. The point is the answer is binary, but irrespective of the answer, you are able to narrow down your search possibility. Okay, a direct question like, is the person Albert Einstein? You will not narrow down the possibilities sufficiently, and most of the time it doesn't work. And the best questions turn out to be that the number of possibilities is cut down in half. Okay, it may not be exactly when you say man or a woman, but well, depending on the possibility, there is a sufficiently narrow down of the choices, and then the number of questions you can ask, how many. Typically, the game ends with about less than 20 questions because 2 raised to 20 is about 1 million, and we don't know those many different names of famous people in our experience. So, how does the optimization work? Well, the two teams take turns. First, one team tries to find out the name, then roles are reversed. The other team will choose a name, and the first team will ask questions, and in general, the team which succeeds in finding the name of the person with the shortest number of sequential questions wins. Okay. So now think about the mathematical structure which is buried inside this scenario. It is something which is known as a binary search. And it's characterized by a possibility that there are only going to be 2 answers, yes or no, and with 2 answers you can only divide the search range in half. Something on one side and something on the other side. And we use this strategy in lots of different contexts. For example, when you are looking for a word in a dictionary, you essentially go by this binary search strategy. Go in the middle, decide it's on this side or on that side, then go in that other part, again this side, that side, and you narrow down the choice until you find what you are looking for. But what happens in that strategy is at every stage, you are able to figure out the reduced database in which you have to search subsequently. And that requires a database which is sorted, just like in a dictionary. Otherwise, you put in, go in the middle, you can't tell it is on this side or that side. In the case of the game which I mentioned, the sorting goes in our head. Okay, whether it is a dead or alive, we quickly figure it out that it is all on this side or on that side. But the sorting is necessary. If it is not available, you can't use this binary search strategy. And what does it do? Well, you are breaking up that full information into smaller questions. The name of a famous person was there, but then you broke it down that dead or alive or man or woman. Those are small questions which will ultimately build up to the bigger question. So the query is factorized. Same thing about the dictionary. You're not looking for the whole word at a time. Look for the first letter. Then you look for the second letter. You break it down into smaller sections and then go and look for it. So if you are able to break down this query nicely in some sequential manner of questions and you have a sorted database, the job becomes much more easy. And this is a generic feature which I had mentioned earlier. Also, you want to calculate a complicated function. Well, if you are able to factorize it in some way or the other, the overall effort required will be less. What is the effort required to sort a database? Somebody made a dictionary, did a lot of work. It was done so that for every user, subsequently, finding the answer is quick. And that sorting requires a lot of effort. This is essentially what Google keeps on doing in the background. Nobody is searching for anything, it just keeps on collecting data over the network, sorts it out in some particular way and stores it. And the query is factorized in a very simple manner. When you type in some question, the only way computer understands it is a binary string, 0 and 1. And then it is matching the string. First 0, second 1, whatever, third, etc., which is a binary search against the database which it has sorted out nicely in some manner. Okay. So it is buried inside, but you can ask how much effort is needed, how much work did Google do? Well, Google needs a whole basically powerhouse to store its database somewhere and maintain it so that when people ask questions, they will give answers, and with all the advertising and etc., they will make money out of the business. So the effort needed is there are very sophisticated algorithm. Well, I can't get sophisticated, but clever enough algorithm which will arrange the database nicely. So, okay, I have to specify what is this, and it is the size of the database. And the naive algorithm which you can construct to say just to sort out numbers in array, which will require comparison of two numbers, which one is larger and which one is smaller, and ordering them, that will take effort which is of order n square. So this one is a much better construction, but that is quite well known and is routinely used. There are algorithms called heap search and well, some other names, etc., which you can find in standard introductory textbooks in quantum algorithms. That is not our main concern, but I just mentioned that this is the amount of work which is needed to sort a database. So now I can ask a slightly different question also, that suppose the sorting is not done. What will be the effort required in that particular case? And to give an example, I can go from describing a dictionary to describing a telephone book. If I say find a phone number of such and such person, it is easy because the names are all sorted and arranged alphabetically, and you can go and look it up. But if I ask the reverse question, this is the phone number, find the name of a person, what will you do? Basically, nothing is available because the phone numbers are not sorted. It is not like the phone numbers is different in one digit, so go and ask a neighbor. It doesn't work that way. So, if the database is not sorted, essentially you can't do anything more than random lookup. It could be anywhere, and you have no idea about it, so you just do a trial and error. And then what is the rate of success? Well, size is n, you just pick up one item randomly, the success probability is 1 over n. Nothing more sophisticated than that. And effort required, well, whatever it is, if you say that I have no more knowledge, I will just keep on doing sequential pickings. If there is no memory, in the sense that I pick one number and try to find the name, doesn't work, then I go back all the way back and pick another number. The number can repeat. I have forgotten what I looked up earlier. And in that case, the effort required is just order n, because it's the reciprocal of the success probability. So, no memory needs I will check exactly answer. You can call it a expectation value or something like that. I will put this average value because it still becomes random, it's a probability. If you have a memory, then I can be a little better job that I have looked it up. I'm not going to touch that one again. Try another one, which is the first time possibilities are n, the second time n minus 1, third time n minus 2, etc. And it goes down that way. So with memory, effort is reduced, but how much reduced? Well, not much. It's basically going from one end to the another, and sometimes it is succeeding early, sometimes late, and in general in the middle. Okay, so more accurately you can count, and the value can be written as little bit more than half the way through, and this brackets of this particular type says that it is the integer value of this particular number. goes one step beyond halfway through is whatever is needed. So this is the situation if you are not given any information and you are just doing random search. So and what is the generic class of this kind of problem? That the problem is in class NP, non-deterministic polynomial. Finding the object takes time, but if you are given the answer, verification is easy. Okay, you will know what you are looking for. Yeah, this is exactly what I wanted. That's the end of the story, and that is a property of any problem in class NP. So this is essentially all I can say, and this is the unsorted one. I should have written down the complexity of this thing as well. So query is factorized. So okay, this is unsorted, and sorted problem with a binary search. So the effort is log to the base 2n. Where does the log 2 came? Because every attempt you reduce the search space by a factor of 2. And starting with n, you want to reduce down all the way till only one item remains, which is your answer. And n to n by 2 to n by 4, etc., etc. You count how many steps are needed, and that is log 2n. And if I want to convert it to integers, I again have to put this truncated number, because these logs are not going to be integer in general, but this is the effort. So yes, there is a gap between having this sorted structure and having an unsorted structure, which is exponential. And that is the reason Google or anybody else, dictionary maker, takes effort to invest time and effort for sorting the database, and then everything else becomes much quicker. Okay. So now let us ask, what will happen to this particular problem when you try to put it in a quantum language? So the mapping is kind of straightforward. These are objects are now denoted by this set of vectors, and they are all distinguishable objects. So this map from the objects to the vectors takes individual items to orthogonal states. Because in quantum theory, orthogonal states are the only one they can be identified with certainly no confusion.
What we are typing on the third part is the properties
F of x, yeah. So f of xi is treated both in classical case as well as quantum case as an oracle. And so you will have a function which is u. I have to, okay, let me call it f xi, which acts on it and gives you the answer. And because we are going to deal with this binary label, because the function is always going to be that answer will be only yes or no. And I can write it as 0 or 1, but as I have done in previous class, it's better to take the unitary operator to map onto either plus or minus 1. It's binary choice. That some case which I want, I can say it is plus 1, and the cases which I don't want, I can call it minus 1. Okay. And now the job is you start here. So at some state inside here, you are allowed to use this operation some number of times. And the final thing is somehow from xi, you should land up at the state which you want, which is xt. Okay. So what is the property of the state? So let me make it specifically by using this particular function. So okay, UF acting on the target state, yeah, that is conveniently taken to be a minus 1, and UF acting on anything else which is not the target is equal to x same. So the target state is one of these possibilities, whatever it is, but we are given this particular function. If you have reached the correct one, it will give you the minus sign. If you have not reached the correct one, that is the plus sign. And then the job is you start let me call S. That after applying this query choice a certain number of times, which I have denoted as this function raised to power q, and well, little bit messing up of the notation, but let not put a f here. That I am going to take some initial state, apply this query transformation many times, The final thing is I should land up with this particular situation. I have to choose some initial state which is convenient, and that is very easily taken to be uniform superposition. You don't have any idea about what the object is when you start. You just give all of the possibilities are equally likely. That's a unbiased statement. So somewhere you are starting here, you want to go there. And all you have is this operator which you can design. Each operator will require some query or some use of an oracle, and it will gradually take you toward this particular state. Some number of queries are used, and you will stop at a suitable number of Q when you have reached the target. And you can identify the target because, as I said here, these are all the NP problems. You can identify that yet I have reached the correct place very easily. Yeah. So now it is a linear algebra problem. Which is, these are unitary operators. This is some unit vector. I can choose all these things to be magnitude 1. So all you can do with a unitary vector is rotate. So you are starting here, you want to this, it will be some rotation, and we have to find out the best way to do that particular task. Yeah.
So we have f of x as the vehicle. Then we have to perform the operations on f of x. But we have performed the operations in the algorithm on states.
Now the operation has to be done on the state vector. Oracle gives you a property.
The problem is we have f of x and we want f x, right?
Yeah.
How can we use x?
Yeah, so you will design this operator and act with that operator on the state, so it will give you the property that you want. Okay, here also I didn't write it down explicitly, but when you do binary search, what will you do? You have two values of fx, say 0 or 1, and you act with that operator on the dictionary you have. Okay, the object on which it acts is the dictionary. Then you apply that, and if you say 0 or 1, it will tell you go this side or you go that side. Okay, so fx is a property, but it specifies the result of an action. The action has to take place on the states. So this essentially becomes the task, and then the question is how well we can do this job. Rotation is a very straightforward exercise in linear algebra, and you can implement it in many different ways, but we are choosing some particular scenario to do that, and I can write down some basis. So the efficient The simplest way to go from S to T, there are two vectors. They are both unit vectors. The operator which you have available is a rotation operator, some type buried inside it. So you just rotate one vector to another in the plane formed by these two vectors. Everything else which is outside, you don't have to worry about it. This is the shortest route, and in geometry it is the geodesic. Okay. So this gives a setting of the problem, and the problem was then solved by Love-Grover in a clever manner, and it turns out to be a use of very simple operations, but also simultaneously the most efficient solution. Most efficient solution in the sense that you can actually demonstrate that under the laws of physics that we have, nobody can improve it anymore. Okay, these are the kind of scenario which are very rare. Most of the algorithms will have a bound, upper bound, lower bound kind of thing. This is the optimal solution. It cannot be improved by any tricks that we know, and that optimality holds not only for large n, it holds for any value of n. So even if the database and things are finite, nothing needs to be corrected in the algorithm, it will work still in the best manner. So these are remarkable properties, but that is why the algorithm is kind of what to call ingenious ways of doing a rather simple problem. Okay. So what did Grover come up with? Okay. How he came up with, I will come later. I will first give the algorithm which will tell you how it works. So for that, let me define this two-dimensional plane. Okay, it's a very simple exercise in geometry, nothing complicated. So I will choose a notation that this T is some vector 1 and 0 in my case, and well, it doesn't matter, and I have to choose a vector which is orthogonal to it, which is 0 and 1. It's only a two-dimensional space. I don't have to do anything more. And right now there is no need to identify it as a qubit or something like that. It's just a two-dimensional ordinary space. So now what is the property which is crucial in making this unbiased choice? And that is this overlap is known, even though we do not know what T is. That is the reason for taking this unbiased choice. Irrespective of which xi you take the dot product with, the answer is 1 over n, 1 over square root of n. Okay, so then I can very quickly write down what is the vector for S. So S will be 1 by root n, which is a component along this, and everything else is in the orthogonal direction, which will be normalized. So it will be square root of n minus 1 by n. I don't have to define what this orthogonal thing is explicitly, whatever it is. I just have to make the overlap correct, and everything else is in the orthogonal component. Okay. So now I'm going to try to do this particular rotation. Yeah.
State is x of t. To get
Yeah.
that's equal to x.
Yeah. Some stage I jumped from writing x of t to t just to, well, cut down on the writing. But what I mean by t is just one of those components which you are looking for. So I start here. I have to go there. And what I am going to perform are only rotations. So I want to get there quickly, so I should take large step to the extent possible. So the distance will be the same. You are starting here, you are going there, whatever the arc length has to be covered, you want to go there. And now I have to design this operator which will take me there with certain number of steps. And what Grover came up with, that he chose this largest unitary steps to be the reflections. Because how far you can go on a circle, the largest distance you go is only reflection. You can't do anything more, one side to the diametrically opposite. So Grover's choice is use reflections. And which are the reflections which he chose is, I will denote the reflection operator by R. So reflection along this direction S, I can write it as identity minus 2 times this outer product. Why this is the operator? Well, if you take a vector along S, this will give value 1 with a coefficient of -2. This will give +1, and the total result will be change in the component along S. Any component perpendicular to S, this will act, it will give 0, and it will remain unchanged. So this is the operator which will reverse the sign of the component along S. And corresponding operator for T, I can also write it as this function. And what will it do? If the component is along T, it will change its sign. And if the component is orthogonal to T, don't do anything. And this directly fits into the criteria which I had assigned to the oracle, that if the state is correct, it will give a value -1. If it is not correct, then it will give you +1. So this is the oracle. So it means quite convenient. This in this language, this fancy oracle just becomes a reflection operator. And this is an extra operator which I need, and even when I don't know anything about T, I can construct this operator because this is unbiased. I know what this state is irrespective of what is the value of T. So in principle, I can construct this operator.
This time we cannot construct this oracle UF. Means RT.
Yeah.
We cannot construct because we
That is given. It has to be the given property of this function which allows you to evaluate this.
property given. Okay.
So now the algorithm is quite straightforward. It's this T is equal to this minus sign should be inside. Okay. I will explain how that comes about, but that algorithm is the statement of what I wanted to do. Start from S, go to T, and I have to repeat some operator in the middle Q number of times, and the operator is designed that every iteration uses one oracle. And this is an operator which is independent of the oracle. So best thing is now to go to the geometrical prescription to see what happens. Okay. So let me draw this two-dimensional plane. I will pick some axis. T is here and T perpendicular is here. And now I have to work out what is the action of this particular transformation. So we want to go there. The vector will be initially somewhere, and we started with this unbiased choice. So let the initial state be over here, and the property is this, that overlap is equal to 1 by root n. So let me write an angle. So this is a cosine of this angle. So it's convenient to write it in terms of this particular angle, which I'm going to call theta. So it's a dot product. The dot product of these two will give the cosine of this angle, which is equal to sine of this angle, and that is 1 by root n. Okay. So now let us see what happens. Initially, this order is designed so that Rs acting on S is going to give identity. It's not going to do anything complicated, so I don't want to act on it. The first action is actually the action by t. What will it do? It's a reflection operator. So the component of the t, component of the vector in the direction of t will change sign. So the state will become this. This is RT acting on S, where this angle is also theta. Component along T perpendicular doesn't change sign. Component along T becomes negative of itself. So that is the action of this. Now I act by RS. Its job is the same, that component along S will change sign if I apply RS, and the perpendicular component will remain unchanged. So, but I put a negative sign in front, so let me do this. So the component along S is basically angle between this one and this one is 2 times theta, and that component is going to change sign. So it's going to, this is just minus S. That component is going to change sign. So let me draw it more carefully. So this is the vector. The component along S will be cosine component along perpendicular to S is not going to change. So yes, it is going to come out somewhere here, and which is RS RT on S. But what I made a life little easier by putting an extra negative sign, which is the extension in this. So this is minus RS RT acting on S, and it is defined by reflection in this. So this angle, by geometry, you can say that between S and this object is 2 times theta. Because that was the angle between S and this, it got changed, and I just brought it back into the first quadrant to make the interpretation easier. So now I can ask, what is the after one iteration? What is the overlap? What is the total angle? 3 times theta. It is pi by 2 minus 3 theta here, but I am writing in terms of this sign. So this angle is 3 theta. So that is what one iteration did. Overlap was this, it increased it. What will happen subsequently? Well, you have to keep on repeating this process. So, not too complicated to go through, but well, I can do it again. Now the angle is 3 theta. So first time I apply it on this vector. Instead of 3 theta being on this side, I will get a new vector which is RT acting on minus RS RT on S, where this angle between S and this is 3 theta. Now this is not an isotope between here. This much, whatever it was positive, that much it became negative. And then I do these other things and flip the component along S and again change the sign on the front side, and I will get a new vector over here, which will be twice. Rotated, and its value is going to be, well, how much is the angle from this one, the same on the other side, and this angle is the same as that, and this angle then will be 4 theta. Whatever is below 3 theta plus theta, it goes that much above. So subsequent now the total angle, if you measure after 2 iterations from this T perpendicular axis, is 5 times theta. So general is progressing in odd numbers. And it's a rotation. How many iterations you should take before you reach over there? So well, its overlap is given in terms of this angle. So you should aim for the rotation being from this axis to this axis, pi by 2. That's it. It's the solution of the algorithm. You can now plug back various things inside it. So you can write this explicit value of Q as pi by 2 theta minus 1 times half. You have to round off because this q is an integer, this is an irrational number, theta is some value given by this constraint, and then q may not come out integer. Whatever it is, you will round it off to get some approximation. That means that the algorithm may not give you exactly t, but it might give you something close enough. So, with how close enough is you have to ask. That you are taking steps which are rotating the angle by 2 theta every time. Okay. And so all the points with interval of 2 theta will be covered. And you want to head towards pi by 2, and there will be some interval you can now choose in which there will be one point for certainty. So, you are changing in steps of 2 theta, and so there is guaranteed to be one value in this interval. And that will be the closest approximation to the integer, and now you can ask. So the error, the algorithm is probabilistic. So the result because you may not land exactly at that particular point, you are sufficiently close and you will stop the algorithm. So after some q steps, and what is the error? Well, the error will be largest error it will be decided by the overlap of this state with the exact answer. So it is cos of pi by 2 plus or minus theta, doesn't matter, because I'm going to take the probability, which means the overlap of this thing square, which happens to be the same as sine square theta, which is 1 over n. So yeah, because you are stuck with the integers and the other parameters may not be nicely arranged, you will stop sufficiently close to it. The angle can be less than these outer boundaries, but the outer boundaries gives you the maximum error, the cosine of whatever that angle square, and which we know. So if you have a database of sine n, the little bit error will come, but the error can be sufficiently small for n, which is any reasonable choice which you are looking at. So this falls into then the class of this bounded error algorithms, where you can get a reasonably high confidence and error is under control. So assume that we will do this. So it will basically take this corresponding value of q and find whatever the nearest integer, and you can express it in many ways using this truncation functions. That is not really important, but now let us see what this produces. I wrote down the answer in this particular language, but now let me convert it into the other variable, which is this n. So half pi tau 2 sine inverse one by root n. I just put in the value of theta. How does this scale? Well, you can make a approximation by choosing that the n is some large number, that for small theta, sine theta and theta are approximately equal. So the sine inverse of 1 by root n will become just 1 by root n, and the algorithm scales as pi by 4 times square root of n. And this has to be compared with the values which are the ones corresponding to unsorted database. Remember that we have not used anything relevant to sorting in this particular analysis. So the algorithm will work equally well whether the database is sorted or not. As a matter of fact, sorting is not necessary. Why? Because you started with an initial state which was a uniform superposition. Sorting will just rearrange this sum, but the addition is commutative. You rearrange in any particular manner, this definition is not going to change. So this algorithm doesn't care about whether sorting is available or not. It will work equally well for unsorted database, and that is its strength, that it can take this situation where classically you are just doing random lookup, and the quantum one is going to do a better job. So it's this is a square root speed up. Which is completely generic, because you have not assumed any property of f. You don't even consider the situation where f can be factorized. You can do better when f can be factorized, but that is a what you call, next step in the analysis. We'll look at it later. But at this step, this just one function specified by just this oracle rule, and you get a square root speed up in the algorithm. And this is quite powerful. And the reason being that you have not assumed any structure at all. And so it will work for any problem in this class NP. All you needed was that verification should be easy. Other than that, you have not assumed any feature for this function at all. It is just some oracle query which is supplied. And so this is a sort of what you call common denominator. You take any problem, you can get at least this much speed up. It doesn't change the complexity class because this square root is like a power law function. It is not exponential, but it guarantees that for any NP problem, you can get at least this much. If you, of course, give more property, you can so it doesn't do anything to the complexity label, but in practice it can help, because if you have something with 1,000,000, you take a square root, it becomes 1,000. In practice it matters.
Any NP problem for searching database.
Any problem, any NP problem is of the like a database. There are a huge number of possibilities. It's a branching process, as I had described earlier in the definition of NP. There are lots of possibilities. And this says that give any function which describes those possibilities, I will find the target. And this is what the result is. And so, yeah, this is a amazing algorithm. Remember that we are using very simple ideas, okay? All that complex number algebra is not there. It's only reflections. And for that reason, the resources which will be needed to implement this algorithm are also much less than generating arbitrary logic gates and things like that. Nothing of that sort is needed. All you need is a capability to implement reflections. So on that side, the algorithm is simple. On the application side, very widespread situation it can tackle. And for that reason, there are what you call classical analogs of this algorithm also available. Because what is reflection? It's available in lots of processes. I throw a ball at the wall, it comes back. Simple reflection. Can it be used in this kind of algorithm? The answer is yes. That will be the like a classical reversible logic version of this process. Well, it can be implemented there as well. Some bit of quantum stuff has gone in, and you have to now identify what that little bit of quantum stuff is in there. It's buried inside, but it can be easily identified. And that requires discussing a very simple scenario, which is smallest solution. So I will describe that very easily. What is the result if I want Q to be just 1? That means after one iteration I'll end up at T. Well, I already worked out the details that after one iteration it has to be sine 3 theta. So that means 3 theta is equal to pi by 2. So which means theta is equal to pi by 6 and n happens to be 4. Sine of pi by 6, 30 degrees is half. So that turns out to be an integer solution. And actually that is the only integer solution. For all the other ones you have to put some bound like that. But the smallest solution is fortunately very easy to describe. What does it tell you? That by asking one binary question, I am picking out of 4 possibilities the correct answer, full confidence, no error. This is very different than binary search. For binary search, with one question you could decide only on 2. Here you are deciding on 4. So there is a factor of 2 advantage even in this little case. Doesn't look like much, but it matters.
So this means then when the databases of science code,
Yeah,
then we can select one out of those 4 objects in one library.
yeah. So now let me write down all the geometrical picture in a different way. And it's basically initial state, which I'm describing as 4 possibilities. What is the amplitude? 1 by root n, which is half. 4 vectors, they are treated as some labels, and here the space, I'm just writing it in a simple-minded notation as 4 amplitudes. Now, I will apply this operator, RT. What was its job? Well, it was a task that it changes the amplitude in sine. Whatever of the 4 is along the direction t. So for simplicity, I will assume that the first one is t and the other 3 are in the orthogonal space. So what will happen here is this is it's a convention, but simplicity. Let me assume that the first one is t. Doesn't matter. It can be rearranged, whatever it is. But this is what will happen. That term will flip in sine. So this is a half and this is minus half. Now I have to apply this other operator, RS. And here I can look at this object as a more what you call statistical meaning. What does it do? It kind of defines the average. So whenever you act by this operator on a state S, it will average all the amplitudes and put the common value inside this average. So initially the average value was half because all the four were equal. Now the average value is different because three of them are plus half, one of them is minus half. So you project it by using this RS and it will change the sign. So it's actually minus RS to a new state where whatever the average is, I will reverse its relative position from that average. So the RS is equal to 2 times S minus I, whatever it is. So the average here is a quarter. 4 possibilities, 3 plus half, 1 minus half. So there is a quarter which is average. And the job of this algorithm is to now flip all the states instead of flipping the component in the original sign, which is what RT did. Flip all the values relative to the average. Okay. So that happens. This is half, average is a quarter, and the reflection basically makes it 0. And this is minus half, this is quarter, and you put it equal distance on the top, it becomes 1. And this is what the algorithm did. That you started with some distribution. This is the oracle. And this is a reflection about average. So at the end of it, the things which you did not want, the one which did not respond to this oracle, they became 0, and the whatever responded to oracle become 1. And that is where you say that for n equal to 4, I stop. If I perform a measurement, here, this is a state which will give me the desired eigenvector with full confidence. All the other components are 0. It will show that this is the vector which will show up on the measurement instrument, and this is my answer. So now what is here which is different than the classical version? It's not very difficult to identify. I mean, I'm writing in a language where all that is done are changing some signs using the reflection operator. Whole Hilbert space or complex analysis, etc. is not needed. The only thing which got used in a very clever manner is interference. That I could change the amplitudes in sign. If there were probabilities, I could not have changed them in sign, but the dynamics is at the level of amplitudes where I could change signs of some of them. And after that, with opposite signs and this calculation of average has done an interference between the plus signs and the minus signs in some clever manner so that the whole amplitude gets focused on whatever I want. Okay. So, interference. And this is the logic which is not available in the Boolean part, where the numbers were all described by probabilities. Here there were amplitudes which could become plus and minus, and the possibility of interference which is there was absent in Boolean logic. So that is the part where quantum feature has gone in, but it tells you that if I can arrange interference nicely in any setup, I should be able to implement this algorithm. And yeah, this is a place to stop, but yeah, I can mention one thing which is not related directly with the algorithm, but very interesting, that this number 4 has a very important meaning for all of us. And it is because we have a database which is organized in numbers or units of 4. We all have it. How it works, we don't know, but it's in our genes. So the encoding of biological information in DNA, RNA, whatever it is a language which uses 4 variables, and the way it works is database search. Whatever is the genes is a lookup table, okay? You don't change it throughout your life. Well, there are some mutations, but ignore them. Whenever you require it, you go and read it. So it is a literally database. You are doing a lookup table, which is a search. And it's not binary search. It's search in units of 4. It's also true that whatever this happens is at the atomic and molecular level. Okay, this is not a database at a higher scale. So whether this structure has anything to do with that fundamental aspect of biology, it's a very interesting question. And I did a lot of work on it in different manner, trying to connect the two. It's a whole theory which is not tested so far. But if you are curious enough, you can look up some of that. I'm not going to do it because it will require a whole new course to be just taught about that aspect of what exactly is the database search in biological processes. But the feature that whatever is there is directly database search, and the best solution which is invented over here fits there. And it is not just the best solution, it is an optimal solution. You can't do anything better. So whether the biology billions of years ago recognized that this was the best way of doing things and put everything in that language, everything which was a competitor lost. That is very common in biology, they just get wiped out. And what we have is an optimal solution. So yeah, with that I will stop today. There are many things buried in this very simple algorithm. I will go through them step by step.